This example steps through the alternatives for preparing a feed example. We're going to look at this heat exchanger in Aspen. It is heating up toluene from 70 degrees Fahrenheit to 450 degrees Fahrenheit with the heuristic pressure drop through that exchanger. So we open up Aspen, add our components. I'm choosing Wilson just because I like it with water. Now we can add our heat exchanger. We want to make sure that we click heat exchanger because that allows us to have the tube and the shell side streams, whereas heater is just the inlet and outlet streams with the utility or some heat demand queue. So now we add our exchanger. Add our streams. So coming in, we have 100 pound moles per hour at 70 Fahrenheit, 20 psia, but we're going to focus over here after the pump. We're going to neglect the fact that the pump is there. So we specify 80 psi. But I'm actually going to multiply this value by 5 just to increase the magnitude to show the use of a shell and tube heat exchanger. So the next input stream would be our heating fluid. Now I'm going to pick high pressure steam. So high pressure steam is available to us at 250 degrees Celsius. And I'm going to choose that the vapor fraction is 1 rather than specifying the pressure. So because we don't have a steam flow rate on this, we take a look at the heat demand. So 2,827,000 BTUs per pound, and in the steam tables we take a look at what steam is at 250 C and or 480 degrees Fahrenheit, and that saturated vapor has enthalpy associated with it of 1204 BTUs per pound. So BTUs per hour divided by BTUs per pound will give us our flow rate of steam required. So I'm just going to round up and say that that's 2,500 pounds per hour of high pressure steam. So since we multiplied our toluene feed by 5, multiply this by 5, that's 12,500. But just for good measure, I'm going to multiply by 6. So we will input 15,000 pounds per hour of steam. So once we specify that, we are now over here in our heat exchange block. So here, similar to the shortcut column and a rigorous column for distillation or scrubbing or whatever separation process, we can have this shortcut option. I suggest using this one at first. This allows you to just see if the heat transfer is even possible in the first place. We want to specify that our hot fluid is on the tube side though. And this is based on a lecture from Friday the 8th of November. But we still need a specification here. And that specification is that the outlet of the heat exchanger is a 450F. So toluene is our cold side, since our hot side is steam. So we can specify in the drop-down menu that our cold stream outlet temperature is going to be 450 degrees Fahrenheit. So after we run it, we can see that in our stream results, everything looks good, or there are no surprises rather. But in this heat exchanger block, we can take a look at the thermal results. So here we can see that the hot stream comes in, or our steam comes in, stream number 3. We get quite a big drop in temperature. We do not get any drop in pressure. So the shortcut column neglects pressure drop. We can see that on the shell side as well. But we're able to transfer all that heat. We can take a look at our temperature enthalpy curves. And so coming up is our toluene, and coming down is our steam. So we do condense our steam in the heat exchanger. Take another look at these thermal results on the next tab over. You can take a look at the balance between in and out, if that matters. But on the exchanger details, this will give us a rough idea of what our actual or required heat exchange area is, and our average overall heat transfer coefficient, and our log mean temperature difference, and any correction factors. So the shortcut just takes everything as more of a back of the envelope type calculation. Now, this is okay for a quick calculation, but if we want to be a little more rigorous, we can select that we want to specify the shell and the tube. So when we click on the shell and tube, it gets converted to a rigorous exchanger. So we just click convert. And our sizing console pops up. So this is, again, the TEMA types that we went over in lecture. So we can see the different types here. We want to have a BEU, E being the most common one shell pass tube, and then our U tube bundle for the other end. And we can change anything in here. This is a drop-down menu of available tube diameters. Now again, this is tubing and not pipe. So, up to 1 inch, 1 1/8, 1 1/4, and so on. Now when we select, say, another one, the actual pitch, this will change for us. So we don't need to worry about it. It'll automatically multiply by 1.25. So we can also select whether baffles or the baffle windows are available to the tubes. The baffle types, gives you a little picture there. So we're just going to leave everything the way that it was. Default, the only thing we did change is the TEMA type to BEU. At the bottom we can select size, and then we'll run through a number of permutations until it finds something that will work for us. So it found one using all of our specifications at the top, or our configuration, and the size that it calculated is a shell outside diameter of 16 inches. So it looks like 0.75 is the difference. So 3/8 wall thickness is what this is going to be. The number of tubes, here we have 154, and we have 2 tube passes, which is why we get this these 2 different red lines as well as blue lines for the tube side bulk temperature and the shell side bulk temperature. Now we can see here that there are also 2 shells in series and 2 tube passes in those shells. It also gives us an excess percentage for surface area, as well as a total cost, just roughly for now, so we can maybe change something and see what the difference is. So if we select maybe 1 inch tubes rather than 3/4, we can size this. And we can see that when we went from 3/4 inch tubes to 1 inch tubes, it did not change a lot for us in terms of cost. However, our shell diameter is the same, but our number of tubes is different. So I'm going to convert back to 3/4, the default. So here we can see these stream temperatures. Now we can copy this image and put it in a report, make it look very nice. We can also do that for our heat exchange, or actual heat exchanger, with our baffles, foot supports, and nozzles, flanges, everything. Now if you want to see what the tube layout looks like, select that one, and these tubes on the bottom half, because it's a U type, they go down this side and they come back. So one side is the supply and one side is the return. So we're okay with this. New design of 0.75, so we want the most recent, not the previous, but the most recent one, and we accept the design. And now we can rerun it because the flow sheet just has the previous shortcut values in all of the streams. So it looks like we have a warning, and there is a potential vibration hazard. So this would require some sort of solution to reduce the vibration or to solve this, but for now we're just going to ignore it. And we can also take a look again at our temperature enthalpy curves. You can see that our increase in toluene temperature mirrors our decrease in our steam temperature. So now we can check the thermal results again, look at our summary, and now since we have switched to a shell and tube rigorous model, it has now calculated a pressure drop. We can see that our pressure drop is just under 6 psi on the shell side, or a cold side, or a toluene side. And on the tube side, we can see that our pressure drop is about 1.5 psi. And this is consistent with boiling and condensing heuristics. We can check our exchanger details. So the absolute required 659 square feet, but with that little bit of over design, so we have percent over or under design, so we're a little over. Now one thing that you can do with the equipment is extend it and actually have it give a data sheet. So after we click on data sheet, it's going to create a new workspace, say heat exchanger example. Now what it has to do is it has to take all of the values from our heat exchanger, stream tables, all of that, and transfer them and map them into something that we can read out in a single document. So it sees that we have 4 streams and 1 block, and so we're going to transfer those into our Explorer option. So the Explorer, we click on the little hard hat after it has been mapped over, so all the values are now tied to everything else. Or rather, the values in the datasheet can be tied to our simulation. So here in our Explorer, we can click our shell and tube heat exchanger and click on this little add new datasheet. And now we can have those values be put into any one of these previous templates. We can make our own, but we're just going to take a look at the templates they have now. So as you hover over them, we have shell and tube heat exchanger. This is shell and tube heat exchanger version 2. So let's just select this one. And here everything is transferred over. So all of our temperatures, flow rates on the shell and tube side have been transferred over, and these are the red numbers here. Now this isn't complete by any means. We would have to go in and put in the tube number, outside diameter, all the construction materials, but everything is right here for you. Now you can also use the textbook website, and clicking on Excel templates will give you all of these options. Now we can download it and have something very similar here. This, if you notice the units, you would not have to switch the units the way we were doing it before. But again, just be aware and be consistent with units and from the simulation to the data sheets. So using a method like this that we have just performed, we can take a look at temperature demand, heat demand, things like that. Now we can also, if we're given a specific heat exchanger, we can specify the log mean temperature differences, the pressure drop, the overall heat transfer methods, and film coefficients. Now this one, as well as the overall heat transfer coefficient, this allows us to put in film coefficients like fouling factors and things like that. Can also specify the outlet pressure based on heuristics or any other metric that we would like. Now for the sake of completeness, taking a look at how much this would cost, this heat exchanger, we can activate capital cost measures. We can see that this system, so the 4 streams with the heat exchanger, almost $1.6 million. Now that's not the full story, because if we click on the equipment, we can see that the actual equipment cost for the heat exchanger, we can purchase it for $36,000. However, the installed cost, as we'll go into next semester, adds $100,000 to that. That also give you the equipment weight and the installed weight as well, because there's a lot of piping, flanges, and all of that goes along with it. So there are factors that you multiply this by in order to get installed weight, installed costs, and other numbers like that. You can also click on the Team Heat Exchanger tab, and this allows us to look at all the other information for a Team Heat Exchanger.